So more often we want to know how a particular material behaves through time as we apply stress or we ask it to deform to a specific amount of strain. So if we are applying a step change in stress to a material, we call that a creep experiment. And in this case, for example, we start at 0 stress. At some point we turn on the stress to a certain level, say sigma naught. We keep it at that stress level until a certain time. This is time t0 and this is time t1. We drop it back to our 0 stress. If we do that for the spring model, then because the strain is directly related to the stress, we end up getting 0 strain until the stress turns on. We get a strain up to a certain point. Then we maintain that until the strain turns off, and then it drops back to 0. So this is our recoverable amount of strain. As I was just writing that, I realized that my graph on the right side was slightly wrong, so I just erased it and drew it correctly. So for the viscous, the same idea, we start out with 0 stress, we apply a constant stress, and then we turn it back off. When we look at the strain through time, we of course have 0 strain until the stress turns on. When the stress turns on, we get it linearly increasing until the stress turns off, and then it stays at that level of strain. So here, our strain at the end of the experiment is set by the amount of time that stress was applied, and this is then the non-recoverable part of the deformation. The other type of experiment that we can do is called a relaxation experiment. And in this case, we are applying a step change in strain at some point t0, and then we turn it off again, or we reduce the strain again at time t1. Typically, when we actually do this relaxation experiment, and the same with the creep experiment, we might just leave it on and look just at the beginning and not at both ends. But for this model, I just wanted to talk about both turning the strain on and off, or as in the last slide, turning the stress on and off. And for the elastic material, again, it's relatively simple that in order to deform that spring or that elastic element by a certain amount, epsilon naught, we have to apply a very specific amount of stress, and we have to maintain that stress in order to keep the elastic element deformed. If we let go of that stress, then the elastic element wants to go back to 0 strain. So we have to hold that stress, and then when we release the stress, at the end, the element will go back to its 0 deformed state. The viscous is a little harder to actually do a relaxation experiment because it's very difficult to apply a step change in strain for a material that really likes to deform according to the strain rate. So in this case, the strain rate here is infinite, because the derivative of this, epsilon through time, which is what is the strain rate, goes to infinity when it's a step change. So what really has to happen in the ideal world, we then apply an infinite amount of stress, which you can't quite do in the real world, but you would have to apply a delta function of stress in order to get the strain that we want to apply according to this equation. And likewise, then it will maintain that, because if you release the stress, it keeps the amount of deformation we've applied. So in order to get it to go back to zero strain at the end, we actually have to apply another delta function of stress, but in this case actually it would be a negative delta function of stress. I drew it here as positive, but it would be the opposite sense, typically, to get it to go back to a zero. So this kind of behavior where we have a linear relationship with strain and a linear relationship with strain rate does mean that when we work with these elements in combination, we have to deal with ordinary differential equations where we have strain and strain rate showing up in the same equation. As you saw in the video and as we've talked about in class, you can combine these elements generally in two ways. In series and then in parallel. So again, we're applying some stress at either end, which would be the same force at either end. And in this case, every element experiences that same stress. The net strain adds. So the total strain is equal to, the strain of element A plus the strain of element B. If we could add 3 or 4, so right now this is A and this is B. We could add multiple dash pots, multiple springs with different viscosities, different spring constants. And so this might have mu1, this might be eta 1. We could add element C plus the strain from element D, and we would have mu2 and eta 2. So we can add as many elements as we want together, give each of them their own mu and eta, and then we can add up put in the equations for how to create these, how these relate to the stress applied, and we can come up with a net strain for these multiple elements. In this case, for this one is called the Voigt model, and this one is called the Maxwell model. The Maxwell model, the same deal. We have a given elasticity there and a given viscosity there. In this case, each of these has to deform at the same rate because they're fixed together this way. So the elongation, if you elongate this as you pull, both elements have to experience the same amount of elongation. So the elongation is the same. So the elongation from element A has to equal the elongation of element B. And in that case, the stress total is equal to the stress of each independently. So again, you can combine these in order to figure out both the creep, which is applying a stress and watching it evolve, or a strain, or the relaxation, which is where you apply a strain and you watch it relax. Okay, I have to apologize. This is just the opposite. This is the Voigt model. This is the Voigt model, and this is the Maxwell model. If we look a little more closely at that Voigt model, so again, we're applying some stress. We have the stress there. We'll give it some elasticity mu and some viscosity eta. The stress of, if this is our element A and this is our element B, the stress of element A through time, so our elastic element is mu times the strain. The stress of element B, which is our viscous element, is equal to the viscosity times that strain rate. If we want to combine these two, in this case, the stresses add together and the strains on each element must ultimately be equal. But we can use the stresses add to come up with our total stress, which is just this element plus this element. So now we've added those together, but again, we have our strain and then our strain rate within here. This would be, so if we apply, if we can do a relaxation experiment where we apply, we give it a set strain through time, we can calculate the stress through time by plugging in our strain and our strain rate, which are known, and we can calculate the stress. So that would be the relaxation experiment. On the other hand, it's sometimes easier to apply a stress when we're doing an experiment. And in that case, we need to work back at what the net strain might be. So this basically requires solving this differential equation, ordinary differential equation, which is a pretty standard one that ends up giving you an exponential. So this would be the result of our creep experiment, where we have some stress applied. So we apply a stress, and the strain through time we get back has to do with this, which gives us an understanding of the elastic component, and then that viscous component applies a exponential change in the material through time. This is not purely the viscous, because this tau actually has to do with the ratio of the elastic and the viscous. And if you review how to solve differential equations of this type, you will see very easily where this tau comes from. It's the It's a direct outcome of the solution for this relatively standard solvable differential equation. This tau, which has to do with the viscosity divided by the elasticity, so the ratio of those, tau is the viscosity over the elasticity. This is what we call the Maxwell time constant. And what it is it for a particular material, if you can understand what the Maxwell time constant is, you can have a good idea of whether or not your material is going to be responding more elastically than viscously or more viscously than elastically. So, for example, if your time constant is, say, 1 year, any kind of stress you apply that's less than 1 year, like a daily variation in the material, is going to be primarily that elastic behavior responding. If you're looking at timescales, changes in this material over centuries to decades or thousands of years, you can probably ignore the viscous response, ignore the elastic response and focus on the viscous response. So for a rock, for example, way down here you might have seismic waves that are an elastic response at the 1 second time scale up to plate tectonic deformation, which would be at the thousands of years time scale. The nice thing about this is that you can further simplify a solution to a problem by knowing whether or not you're within this purely viscous range of the material behavior or you're down in this purely elastic range. And you can simplify the mathematics accordingly by making an assumption about the viscosity or the elasticity and just dropping those out of the equations. You need to be very careful to be clear what those assumptions are and how far you are from that Maxwell time constant, because anything that's happening in the middle here near the Maxwell time constant, you probably need to include both elastic and viscous. And every material will have a different time constant. Some might have a time constant of a few minutes. Some might have a time constant of decades to hundreds of years. But you can figure out the time constant by looking at the ratio of the material properties. So this is still that Voigt model where we have the two elements in parallel, the same ones that we were just talking about. Where the stresses add and the net elongation is the same. So if we do the creep experiment here, we apply a stress at a certain time and then relieve that stress at a certain time. When we apply that stress, the elastic element wants to jump right directly up to its full extension, but the viscous material is causing it to not be able to jump right up there. So the viscous element in this case causes it to more slowly elongate, but its final elongation is still going to be related to the spring element that defines this epsilon naught that's our final elongation. When you relieve the stress, the same thing happens. The spring wants to jump back right away to its 0 point, but the viscous element causes it to do that very slowly with an exponentially decreasing strain. So the thing to note on this is that while there is a viscous element in there, it still is recoverable strain. So this is what we call delayed elasticity. And most materials have some amount of delayed elasticity in them. They can never, in the perfect world of a spring that responds instantaneously, does not really apply to a crystalline rock material where it really does need some time to respond in order to get up to elongating those bonds and creating that deformation. If we do the opposite, this is our relaxation curve. So we apply a step change in strain, or we force it to strain at a certain amount, and then we force it back. Because we're forcing it, we actually have to apply our delta function of stress to get that strain to happen. And then similarly, when we want to close it, reduce the strain back to 0, we have to provide the delta function of strain to finalize that. So this is something that is very difficult to demand in the real world, but that's the idealized process that has to be happening. Because of the viscous element, we have to have this delta function. The strain then is elongated, and then to return it back to 0, we go back to that 0 point. So the other model in series is the Maxwell model. And again, we have an elastic element. Let's do that in purple. And we have our viscous element. In this case, the total strain is the net of both of them, but it's much easier in this case to add the strain rates than to add the final strain in terms of the mathematics, but you could do either. So here we have the total strain rate is equal to the stress rate, so that this is a dotted stress for the elasticity, so we've just taken these and turned them both into rates, and our stress here is just the absolute stress, not the rate of change of stress with the viscosity. Again, this is a solvable ordinary differential equation, and the final stress looks like this, where the stress is equal to the stress at this amount of stress times the exponential function, which again is related to the Maxwell time constant. If we run these same experiments and look at them graphically here, we can see again the creep and the relaxation for the Maxwell model. So in the creep experiment, we're applying a set amount of stress and then taking it off. Here, when we apply the stress, the spring will respond instantly, and then the viscous material responds with that linearly increasing strain because of the strain rate. When we take off the stress, we get back the elastic, but we don't get back the viscous. So this change in the elastic there is the same as this change, in the strain there. And our final strain, the final strain that we get, is actually this amount of strain, because that is the non-recoverable strain. If we do the relaxation experiment, we apply a step change in strain, which the spring likes. So the spring is we force the spring into a certain, we elongate the spring a certain amount, and we will have to apply a certain amount of stress to get it there. But after we apply that, the viscous material, the stress then transfers over to the viscous material, and the viscous material starts deforming. So even though we keep this steady, what's happening is that this net strain, where the strain is equal to the strain of the elastic element plus the strain of the viscous element, the initial strain is all this elastic element, but eventually all of that is transferred over to the viscous element, and the stress pretty much drops to zero because that ends up being a non-recoverable strain. So we have a net strain that we're left with at the end that's the viscous, that was the viscous amount of strain. If we then try, because we've now relaxed the stress back to zero, if we want to try to return that strain back to its 0 point, I want you to think about what has to happen in this box. And this kind of relates to what your computing assignment is. So what happens next? It's not necessarily a simple mirror image of the turning on the strain, because we've now relaxed and created this as which was initially a recoverable elastic strain. By the time we get to this point, it's been a permanently deformed viscous strain.